Hello students. So today we are going to do exercise 1.2. Okay. Exercise 1.2 first question. Show that the function f from r star to r star defined by f of x equal to 1 by x is 1 1 and on 2, where r star is a set of all non-zero real numbers. Means 0 is removed from this r. Okay. Is the result true if the domain r star is replaced by n, that is set of natural numbers? Okay, so function is given. I'll write here r difference 0 because all non-zero numbers they are saying, right? Defined by f of x equal to 1 by x. Okay, now they have removed 0, so we will not get infinity, right? 1 upon 0 is infinity. So starting with 1 1, let f of x1 is equal to f of x2. So 1 upon x1 is equal to 1 upon x2. So multiplying you will get x2 equal to x1. So this is 1 1. Okay. Now second we have to prove it to be onto. So for y belonging to r difference 0, we'll write f of x is equal to y. Okay. F of x is what? 1 upon x. So y. So 1 upon y is your x. Okay. Now you have to put this x in f of x. So f of x is equal to 1 upon x. So f of 1 upon y is 1 upon 1 upon y. So this is y. So we are getting it to be true. Okay. So there exists for all y belonging to r difference 0, there exists x belonging to r difference 0 such that f of x is equal to y. So it is onto. Next condition they have given is you have to replace domain by set of natural numbers. Okay. 0. Same function, it is f of x equal to 1 by x. So 1 1 is true. Okay. We have to go for onto. So for onto means these are all real numbers, okay, and these are all natural numbers. So 1 2 3 4 5 and so on. So here in between 1 and 2 there will be some numbers like 1.5 1.3. Okay, so these are not mapped, right? Because if I start from 1, so 1 by x, so 1 by 1 is 1 is going to 1. Okay, 2 is going to half, 3 is going to, okay, 1.5 is mapped. 3 is going to 1 by 3. Like this it is. Okay. So, yeah, into this bigger numbers also you can take 4, 1 by 4. So, starting from 1, you will get 1 point, this is 0.5, not 1.5, 0.5. Okay. So, you'll get numbers which are 1 and less than 1. That is 1 or less than or equal to 1. Okay, in this set. You will not get numbers like 1.2, 1.3 that is greater than 1. You will not get. Okay. So, here the numbers are mapped from This is your 1 is going here, 2 is going to 0.5 and so on. These all are mapped. But the numbers like 2, 3, 4, then 1.2, 1.5, these are not mapped. This remains. So it is not onto. Okay, so you can write for say 1.3 belonging to R. There does not exist x belonging to n such that f of x is equal to 1 by x. Okay, you can, this is your example to prove that. Okay, second question. Check the injectivity and surjectivity of the following questions. Okay, from n to n, that is a set of natural numbers f of x equal to x square. Okay. That is, we have to check for 1, 1 and on 2. Now this is a set of natural numbers. Okay. So 1, 1 f of x1 is equal to f of x2. So x square is equal to x square, x1 square, x2 square. So x1 is equal to plus or minus root of x square, that is x2. Okay. Now here negative numbers are not there. That is, if you are taking 1, it will go to 1. If you are taking 2, it will go to 4. If you are taking 3, it will go to 9. So all are mapped and it is 1, 1. Okay, this is 1, 1. Now for second onto 1, 2, 3, 4 and so on. 1, 2, 3, 4, 5, 6 and so on. 1 is going to 1, 2 is going to 4, 4 is going to 16, 3 is going to 9. So these numbers are left out. So you can write for any 2 belonging to natural number, there does not exist x belonging to natural number such that f of x is equal to x square. Okay, so it is not on. Second one, it is a set of integers, all positive and negative numbers. Okay, now in this you will get a negative number as well as positive number. Okay, so f of 1 you'll get 1 and f of minus 1 you'll get again 1. So both are going to the same number. So this is many 1. This is not 1 1. Not 1 1. Okay. Then for on 2, here on the other side, that is z, you will get only the positive values and negative values will be left out. Okay. So you can take for minus 2 belonging to this, there does not exist any x belonging to this such that f of x is equal to x square. Okay, so it is not on. Next one. F from R to R given by f of x is equal to x square. Okay, this is a set of real numbers. Real numbers all are there. This we have done, I think. Here also same thing because negative numbers are there. So f of 1 is going to 1 and f of minus 1 is going to 1, not 1 1. And for onto also you can write the same thing as we have done for this integers. Okay, for -2 there is no number in the domain set such that it is f of x is equal to x square. Okay, then fourth one, f from natural numbers to set of natural numbers given by f of x is equal to x cube. Now cube is there. Okay, a cube means now this is a natural number, set of natural numbers. So f of 1 is going to 1. Okay, f of 2 will go to 8. Okay, so this is 1 1. This is proving to be 1 1. Okay, 1 is going to 1, 2 is going to 8, 3 is going to 27. Okay, then we have to check for onto. Now for onto, in between these numbers, that is 2 is there, 3 is there, 4 is there, right? So for 2 belonging to n, there does not exist any number belonging to the domain set such that f of x is equal to x cube. So this is not onto. Okay. Next, they have taken set of integers. Integers means all positive and negative values. F of x is equal to x cube. Now we know that negative cube of a negative number is negative, right? So f of 1, if you take, you will get 1. F of -1, you will get minus. Okay. So this is becoming 1 1. Okay. So this you can write 1 1. Okay. So you can write it as, let say f of x1 is equal to f of x2. So this is x1's cube is equal to x2 cube. So x1 is equal to x2, and you can write here some example. Okay. Then proving onto. So for onto 1 minus 1 2 minus 2. 1 is going to 1, minus 1 is going to minus 1. 2 is going to 8, minus 2 is going to minus 8. So in between there are some numbers like 2, then 3, minus 2, minus 3. Okay. So these numbers are not mapped. So for say 2 belonging to set of integers, there does not exist any x belonging to z such that f of x is equal to x cube. Okay. Let's solve the next question. Question number 3. Okay. Prove that the greatest integer function from a set of real numbers given by f of x this is neither 1 1 nor onto. Okay. Denotes greatest integer less than or equal to x. Okay. So it is defined as f of x is equal to this. It is less than or equal to means if I take number say 2.5, okay, then less than you will get 2. Okay, for 1.9 you will get 1. You have to take the lesser integer than this number. Okay, so you have to prove it to be not 1 1. This is proved, right? So if I take any number say 1.5, 1.4, 2.9, 2.3, okay, this will go to 1. This will also go to 1. This will go to 2. This will go to 2. So from here we can say that it is not 1 1. Okay. Next is onto. Now the numbers are mapped to only integers and here real numbers are there, right? Like this 1, 2, 3 and so on. So these are mapped to only integers. In between there are many numbers, 1.5, 1.6. These numbers are left out. Okay. So you can write that for say 1.5 belonging to R, there does not exist any x belonging to R such that f of x is equal to greatest integer function. Okay, so it is not 1 1 nor onto. Okay. Next is question 4. Show that the modulus function. Okay, modulus function given by f of x equal to mod of x. For the functions, that is the introduction of functions, you can refer to my relations and functions for standard 11th. Okay, there it is given in detail what are the functions and different types of functions. Modulus function is neither 1 1 nor onto. If x is positive 0, x is negative. Okay, so this function is defined as x minus x if x is greater than or equal to 0 and if x is less than 0, right? So we know that if you take 1, when it goes inside the mod, you will get a positive number. If you take minus 1 inside the mod, you will again get a positive number, right? So 1 is going to 1 and minus 1 is also going to 1. So this becomes many 1. So it is not 1 1. Okay. Let's write for onto. So this the codomain is whole of R, means there are negative numbers also, right? And this function is going to positive numbers only. So if you take 0, 1, 2, 3, minus 1, minus 2, these negative numbers are left out. Okay, that is minus 1 is going to 1 and 1 is also going to 1. Minus 2 is going to 2 and 2 is also going to 2. So all the negative and positive numbers are going to the positive numbers. So negative numbers are left out. So you can write for say minus 2 belonging to R, that is this set, there does not exist any x belonging to R such that f of x is equal to mod of x. Okay. Question 5. Show that the signum function f from R to R is given by, okay, signum function is defined greater than 0, equal to 0, less than 0. Okay. Now from this only you can say that it is, if you take 1, you will get 1. If you take minus 1, you will get minus 1. Okay. But if you take any number greater than 0, 2, it will go to again 1. So this 1 is going to 1 and 2 is also going to 1, 3 is also going to 1. That is all positive numbers are going to 1. Okay, so this becomes many 1, not 1 1. Okay. For onto, the range set is only 1, 0 and minus 1. Remaining numbers are left out, like 1.5 you take belonging to R, that is codomain. There does not exist any x belonging to R such that f of x is this signum function. Okay. Question 6. Let A be 1, 2, 3 and B 4, 5, 6, 7. Let f, this is a function, Okay, be a function from a to b, show that f is 1 1. Okay, so a set is 1 2 3, b set is 4 5 6 7. Okay, I'll draw the diagram. So function 1 is going to 4, 2 is going to 5, 3 is going to 6. Okay. So can directly write this as f of 1 is 4, f of 2 is 5, and f of 3 is 6. These are distinct elements, right? So this is 1 1. Images are distinct. Next question. In each of the following cases, state whether the function is 1 1, onto, or bijective. Justify your answer. Okay, your functions are defined. So f from R to R, f of x is equal to 3 minus 4x. Okay, so first we have to prove 1 1. So let f of x1 is equal to f of x2. Okay, for x1 x2 belonging to R. So we have 3 minus 4x1 is equal to 3 minus 4x2. So 3 goes 4x1 minus 4x2 minus 4 4. So x1 is equal to x2. So this is 1 1. Okay. Now for onto, say take some, let y belongs to R. Okay, such that f of x is equal to y. F of x is what? 3 minus 4x equal to y. So minus 4x equal to y minus 3. So x is equal to 3 minus y upon 4. Okay. So no problem of infinity because here 4 is there. Okay. So for all y, this is possible. So this is onto. Okay. So you can write that f of x is equal to y, that is 3 minus 4x. So in place of x, you have to put this 3 minus y upon 4. So 3 minus 4, 3 minus y upon 4. 4, 4 gets cancelled. So 3 minus 3 plus y. So you are getting y. So this is onto. Okay. Next is f from R to R, defined by f of x is equal to 1 plus x square. Okay, start same way. Let's say f of x1 is equal to f of x2 for x1 x2 belonging to R. So 1 plus x1 square is equal to 1 plus x2 square. 1 1 gets cancelled and you'll get x1 square is equal to x2 square. Then x1 is equal to plus or minus root of x2 square, which is plus or minus x2. Okay. So you are getting plus x2 and minus x2. So both are there, right? So for example, you can take f of 1 is going to 1, 1 plus 1, that is 2. For f of minus 1, you are getting 1 plus 1, 2. Here 1 is going to 2 and minus 1 is also going to 2. So this is not 1 1. Okay. Now for on 2, let's say y belongs to R such that f of x is equal to 1 plus x square is equal to y. So x square is y minus 1, x is root of y minus 1. Okay. So this number should not be minus. So if I take say minus 2 minus 1, so you'll get minus root 3. Okay, and this does not belongs to R, right? So you can write that for say minus 2 belonging to R, that is the codomain, there does not exist any x belonging to R such that f of x is equal to 1 plus x square. Okay.